What is the most used man-made material on Earth? You guessed right, it's concrete. Look around. It's everywhere. Sidewalks, driveways, foundations, floors you stand on, and even entire buildings are made out of concrete. So why don't we discuss it more? In each episode of Concrete Logic, we will explore one concrete-related topic with the help from industry professionals that are shaping the future of the trade. We'll talk with suppliers, contractors, architects, engineers, specialists, and even some proponents of competing materials about their views of concrete and their vision of its future. Welcome to another episode of the Concrete Logic Podcast, and today I have Bill Kulish with Steelike. Did I hit the last name correct?
You nailed it.
Yes, I landed it. Nice. Bill is my expert on ultra high performance concrete / composite, which we talked about that last time. So Bill has been on the podcast twice before. Episode 34, Amped Up Concrete, back in early 23. And then again, last November, episode 66. Titled UHPC, Not Your Grandma's Concrete. So check those out. Those were both great episodes. Give you an intro into UHPC, or ultra high performance concrete. Before we get started with our conversation today, just a reminder how you can support the podcast. There are three things you can do. One is share the podcast with a colleague or coworker in the industry. The second thing you can do is if you go to concretelogicpodcast.com, and there's two ways of getting a hold of me. You pick your poison. One is you click on the little contact button there on the homepage, and you can leave me a message. They'll shoot me an email. And then the other way is in the bottom right-hand corner of the homepage, concretelogicpodcast.com. You can leave me a voicemail. There's a little microphone there. Click on that, and you can leave me a voicemail. And then the third way, back to that homepage, there's a nice blue button on the upper right-hand corner. It says donate. You click on that. You can give any amount you want. And like I say on every episode, it doesn't matter how much you give. It just tells me that you're listening and that you enjoy the podcast. So feel free to do that as well. Today's episode looks like episode 89. So there's quite a bit of content there. So please check out concretelogicpodcast.com, and you can check out all the episodes there. With that, Bill, let's get into it. So Bill, like I said, Bill is the chief, I think he's titled president, chief technologist, founder of Steelike. Works exclusively on ultra high performance concrete or composite, whichever nomenclature or whatever we're going to call it today, Bill.
That's fine.
So where do you want to start today? I know we were talking before we hit record. So we're all chasing this reduction in concrete's carbon footprint, and there's the powers that be that are requiring that, if be it a governmental agency or clients, and there's all kinds of incentives out there floating around that reward folks that can show that they're reducing their carbon footprint. So the concrete industry is no different. If you want to talk a little bit about what you're seeing and how UHPC plays into that, let's start there.
Sure. And thanks for having me on, Seth. And I often watch your podcast. I learn from other experts. I'm one of many experts with UHPC. All my respected colleagues and competitors that actually have certified UHPC, not a YouTube video recipe that doesn't work on a bridge. We're all embracing the challenge, at least in the United States. To the best of my knowledge, we're the only country that's doing this. Let's let's displace one thing with another to reduce the carbon footprint. So I'll just briefly go over, for your guests that haven't heard much about UHPC, what it is and how it's different. And then I'd like to touch briefly on how we can reduce the carbon footprint in multiple ways by correctly utilizing UHPC where it makes sense. It's one of those things where just because you can do something doesn't mean you do something. So quite often you're not going to see stadiums, high rises, or entire roads other than potentially some bridges made out of UHPC, ultra high performance concrete. We have our standard mixed designs that have been around for decades, and on average, 4,000 to 5,000 pounds per square inch is required to cause a failure. Strength's important. It's one factor. Take a porcelain plate out of your cabinet. It might be 45, 50,000 PSI. You drop it, it shatters into a million pieces. You wouldn't use a porcelain plate to hammer a nail in with. You would use a hammer. Using the right tool in your toolkit as a contractor, a specifier, a bridge design engineer, a bridge owner, it's paramount. And it's wonderful if you can use a material that lowers the carbon footprint. Concrete, we all know, requires a lot of heat to make glue, cement. And cement is just one of the many glues that myself and colleagues have used in the design of ultra-high performance composite concrete. Some of the glues have nothing to do with cement other than they are in the binder family. So when we're talking about water-cement ratio, common term, in UHPC world, we talk about the water binder ratio, W/B. Anything that activates, that crystallizes, that hydrates is a binder / glue. And I mean, there are concretes that have no cement, alkaline reacted. There's concretes that have extremely high cement content. ECCs can be over 55, 60% glue. And then there's your Quickcrete bag that on average is 20% glue. The rest is ags.
Pause there. What you just said something. ECC. What is that?
Sorry. It's engineered, self-leveling, self-consolidating, very flowable. Technically, you would almost call it a mortar. You could technically call UHPC a mortar because it doesn't have any big aggregate. So it's engineered concrete that quite often is being used in replacement of a grout and such.
Okay.
Very high. Historically, much more binder cement than UHPC. Where our differences come in with ECC and Home Depot Quickcrete or Lowe's or whatever you have in your neighborhood is we do have a higher amount of binders, of which only one of them traditionally is Portland cement. We do use, on average, 40 to 45% of any of our UHPC mixed designs are binders. A good percentage of those are displaced with post-industrial waste. Not sharing my recipe publicly, but some of those binders in mine may or may not be, and in other materials may or not be fly ash, silica fume, volcanic ash, slag, metakaolins, any of the pozzolanic reactive materials. Anything that when you add water hydrates, creates an exothermic reaction, right? So that's good. That's your glue. And we all need to have glue. Now we need to get into the particle packing. What makes UHPC unique, and my simplest analogy for those that don't know, and I apologize in advance to those that do know, is you take a 5-gallon bucket. How many bowling balls can you put in there? 1.5. What's left out? What's left over? A lot of air. So you say, okay, I want to have less air. You take the bowling balls out, you put in volleyballs. You take the volleyballs out, you put in baseballs, you go golf balls, you get down to BBs. You're like, oh, good, I can fill this whole thing with BBs, particles. I can fill this whole 5-gallon container with BBs. I still have a lot of air. So I'm not going to take all the BBs out. I'm going to take some of them out. And in fact, in the beginning, I may not need to take any of them out. I'm going to put in smaller balls and smaller rectangles and trapezoids and all kinds of different shapes. And eventually, I'm going to have just about no air. So two things, at least with today's physics, two things can't exist in the same space at the same time. So when you take, and this ties in, Seth, believe it or not, it ties into reducing the carbon footprint. So you can't have two particles occupying the same space at the same time. But you need that bucket, when a little bit of water is added, you need to have very little air. You need to have a non-contiguous pore structure. You don't want a whole bunch of anthill tunnels going to the surface that will then let water in that could freeze, or chlorides that would create issues with steel. And you just keep going and going and going, and that is the high-level view of particle packing. So a true UHPC is much more than high binders and a bunch of aggregates. It's multiple different types of binders. Again, some of which are post-industrial waste, are things that were thrown away years ago that they found out have good benefits. And you need different sizes of those molecules. You need different sizes. Cement's like 100 microns. Silica fume could be 10 microns. There's things that are submicron. And when you get enough of them reacting at different times and generating different amounts of heat, almost like a time-delayed fuse or a time-delayed bomb, and you have micro bombs going off at different times, you can control the rate of hydration. You can decrease it spiking way up. Like if you buy Rapidset, you put it in a bucket, you add water, within a couple minutes, the pH goes to 14 and the temperature can jump to 100 plus and just keep going, 300 degrees. And then what happens? It's got to cool down. And when it cools down, you have all this expansion, contraction. It's just a circus of physics, where with UHPC, if it's designed correctly, they tend not to spike as high, and they go up gradually, and then they also come down gradually because they're reacting on their way up. Some of the stuff is and is not, and some of the stuff's reacting on the way down. So, in summary, UHPC in my right hand will last 75 plus years. Conservative is 75. They stuck a bunch of piles in brackish water up north for 20 years with UHPC with steel inside. Tides coming in, freeze thaw, water, everything you can imagine, chlorides. They dissected it 20 years down the road. This is all publicly available. I'll get the link to Seth. And the ingress was like 1/4 of an inch. So the water, the salts, the steel inside was shiny and new. It's like biting an apple in a vacuum. If there's no oxygen and there's no moisture, you're not going to get oxidization or rust. So we have UHPC over here. It's very expensive. Last 75, that study predicted, it hasn't been around that long, it could be 1,000 years, right? But let's just stick with 75 years to be conservative. Its tensile properties are off the chart. It actually exhibits, with high tensile steel fibers, it exhibits strain hardening. You put a load on a beam, you'll get your first crack. But what you're not seeing prior to the first crack is millions of microscopic cracks. The cracks are so small that water can't get in. So the material isn't bending, it's cracking. But because the cracks are being redirected in so many different directions, and the cracks aren't running into a 3/4 inch piece of stone with veins in it, and because of the correct particle packing, the cracks are forced to propagate in multiple directions. You finally see a crack. It doesn't fail. In most cases, after the first crack, you can continue to apply the load and in many cases exceed the load that caused the first crack, strain hardening. That would be one of the biggest difference in my right hand, UHPC. Throw this in the ocean, come back in 1,000 years, power wash it. You're not going to see a change. We won't be alive, but science says that, right? Over here. Freeze thaw. The more you freeze and thaw a true certified, tested, vetted material that's been used on U.S. infrastructure, the better it gets. It starts off at 100%. After 600 cycles, it goes to 104%. I know it's counterintuitive. Abrasion resistance. It'll wear down the abrading pad. It's innocuous. So, in summary of the material, chloride's below 50 coulombs, innocuous. Highway stuff might be 4,000 to 3,000. ECCs could be in the thousands. UHPC generally is under 150 coulombs. What does that mean? Well, they take a bar and they put voltage through it. They measure the resistance, and they can extrapolate the resistance with the amount of chlorides getting into the material. So, Seth, I'm going to take a breath, but that's a high level of some of the differences. And, we can talk strength all day long. I've had stuff break over 30,000 PSI after a year. On average, 21,000 in 28 days. If you add heat, the FHWA did a girder project led by Ben Graybiel, and we went to a precast fab in Pennsylvania. They had a steam bed, 30-foot girder, 2-inch web, 6 feet tall. They monitor the bejeebies out of it. They brought the bed up to 135 degrees, and within 7 hours, it was 14,000 PSI. Yay. What does that mean? Well, it means that a precaster could turn over a lot more material and free up his expensive molds on a daily basis. But now that girder can be put just above sea level and be exposed to very abusive caustic environments that would rust out metal over time. And it's only going to get better, ironically. So I'll stop, take a pause. I tend to get excited about this material.
Well, it's what you do for a living. You should be excited about it.
Drives my wife crazy. She's like, that's great. What are we having for dinner? You don't understand. We can do this with it. Uh-huh. That's fantastic. Can we take the dogs out for a walk?
Yeah. No, I think you commented about we get excited about the strength of concrete or how fast it gets strong or things like that. But a few episodes ago, I had Robert Higgins on, and we were looking at a chart that he has of normal traditional concrete and the temperature of the surface of the concrete at the time of when curing begins, and we looked at from 70 to 80, 91. I think 120 was the high end, and what you find is the higher the temperature, the more detrimental to the strength of the concrete it
Yes,
is.
sir.
So, does UHPC, is that I heard you mention that you have results from after a year, which in traditional concrete world, there's not a whole lot of people that are looking at concrete strengths after a year. So who knows what we got? I'm sure there's some folks out there, researchers and folks that aren't in the industry. Let's say the tradesmen that do it day to day, and ready-mix suppliers and those guys. I don't think there's a lot of them that are out there taking tests at 365 days after placement. So I guess why did you do that? And two, does UHPC act the same as far as temperature? The higher the temperature, is it more Is it detrimental to the strength of the concrete or the durability of concrete, of the UHPC?
All good questions. I'll go out of order as my dyslexic mind is wired, but I can answer them. Temperature first. So as I mentioned, we're using many different types of binders, all of which are different sizes. The smaller something is not generally, the more surface area it has, and ergo it tends to react more than a bigger particle. By particle packing, not just for the physical displacement of air, but to form non-contiguous channels, a binder uninterrupted by big blocks of faulted, think drywall, you score it, you crack it. To me, that's what a 3/4-inch stone is. We're not analyzing every stone we put in. There's fault lines in that stuff. I mean, heck, it was sometimes dynamited to make it, if not crushed. So we could be, the load hits that fault line and it snaps like a piece of drywall. But temperature-wise, we have so many different binders going off at different times, different intensities of reactivity. And we have quite often these metal fibers. Well, metal fibers dissipate and uniformly disperse the heat. So the cement in my material is one of the last things to hydrate. So I have other things going off. So they're doing what they do and kind of pre-warming things, right? So you get less of a thermal shock. UHPC, uncharacteristically, compared to traditional concrete, generally ramps up very slowly. We rarely start to even see final set until an hour and a half to 2 hours. And it's cold, and then it's warm. But it's not going to be you can fry eggs on it. Now, of course, mass plays an important thing. We did a SEPTA project where we encapsulated a steel girder that had about 70% life left in it. So SEPTA wisely chose to clean it, dig it out, clean it up, and then encapsulate it with approximately a 3 cubic yard box to encapsulate that rust. So the UHPC went in the holes and replaced the steel, and then it's further protecting it from degradation because of the chloride resistance and everything I talked about, Seth. And that thing got hot, but it didn't get hot immediately, and it ramped up over a day's period. Now, in 12 hours, because of the amount of mass that was surrounding it, it already hit 14,000 psi. And then it started ramping down. It took about 3 days. But the spike we saw was in the mid 100s. And then it was still warm 2, 3, 4 days after that versus traditional concrete, which I've seen get well into the high hundreds, mid hundreds, and then just drop down. So what's happening to that steel bar that's in there? Well, you can use a lot less of it with UHPC, but let's pretend we have a box full of traditional bar that's needed. And we put in traditional concrete on the right, rapid set in the middle, and UHPC on the left. Well, the one on the right has a pretty good chance, but physics say it's going to heat up, and it tells us the concrete's going to cool much faster than the bar. So the bar is going to be retaining heat. What is that bar heat doing to the immediate surrounding area of the material? Well, it's stressing it out. And then you get into expansion contraction coefficients, and you get into the tensile properties. And quite often you've already baked in a lot of micro cracks that may or may not connect with air channels, that may or may not let water and chlorides in. And then it freezes and thaws. And wow, my dog is singing. And then it connects and you have potentially an issue. The rapid set's going to really spike. Rapidly spike. The pH is going to go off the charts and it's going to drop as fast as it goes up. Pretty good chance you're going to have some shrinkage challenges and micro cracking. Again, we have just two completely different expansion contraction coefficients between the metal inside and the material itself. And then you have UHPC over here. And it's not a miracle lava. It simply is the way it's designed, or a byproduct of why it's designed. The material ramps up very slowly. It hits its peak and it kind of hovers there. And then it's still reacting, but different things are reacting as it comes down. So in one case, you have massive reaction and stopping. You have an elevator going up and an elevator coming down really slowly, stopping at each floor. So that would answer the temperature statement. And Seth, could you pull me back in with the other two questions?
The temperature we were talking about, I think what you're getting at is it doesn't have a negative impact on UHPC like traditional concrete. Yes or no?
Yes, sir.
No.
That is correct.
So the strength isn't. Yeah. So the strength of the concrete is not impacted by the temperature. So I forgot what else I was asking you, but the big pushback on UHPC is the cost, right? It's expensive.
Absolutely.
Also, the quality control for UHPC, I imagine, is a lot higher than traditional concrete. I mean, traditional concrete. I mean, there's guys pouring sidewalks and driveways every day with it. It's very easy. There's no special handling, but with UHPC, I imagine there is. Can you talk a little bit about the cost and the quality control?
Definitely. I'll do quality control first. So quality control with UHPC is paramount. Unlike sidewalk concrete and many roads and bridges, we're not putting in a scoop of orange, wet, damp sand, throwing a bag of Quikrete and some rocks. That sand alone, other than potentially causing alkali silica reactions, you might pay $15-$20 a ton for that kind of sand that's often used. And the problem with it is it has impurities. It's colored because of the impurities. It might have a lot of iron in it. It certainly has moisture in it. So we have to we consciously have to choose a consistent grain size, and it has to be pure. And
so
really
let me stop
go ahead,
you.
sir.
I think this is what you're getting at. We'll kind of simplify this for the listeners. So when you're producing UHPC, you're really taking care of the products that you're putting into UHPC versus ready mix supplier. He orders aggregate, he orders sand. It has to meet some. I believe Dr. Belkowitz is going to kick me in the butt if I don't say this right, but it's got to pass certain ASTM standards, right? For them to use it. But it's a wide range.
Yes.
So the aggregate and sand shows up, goes and sits in the yard. The cement shows up, and it's got some kind of certificate on it, and it says what it is, but the cement supplier doesn't have to tell the ready mix supplier, the ready mix producer, how they made that cement, what additives and things they use to produce the cement. So really, we don't know what's in that cement, if we're all being honest with ourselves.
Correct.
So that shows up. So and then of course water, and we'll just stick with those 4 or 5 ingredients of a traditional concrete. So all that stuff is thrown in a truck, and the truck spins and goes. I mean, it's not doesn't take special handling to make concrete, right? Traditional concrete. So, but what you're saying with UHPC, it's very hands-on on what goes on there, right? It's the top of the line material that you're putting in there. So you won't tell us exactly what goes in there, but so it's got a lot of cement in it, right? So I imagine
It's got a lot of binder. It's got a lot of binder.
Okay, so we won't say. So it's got to have cement or slag or fly ash, right? Am I beating around the round bush?
No, not at all. Yeah, you're fine.
No, am I in the ballpark? So it's got to
Yes, sir.
have those things, and and those things are you're very highly selective on what you're putting in there, right?
Yes.
Okay. Versus a traditional concrete, we're looking for the cheapest thing to put in there. We want
Yes,
cheap.
sir.
Yep, that's how
Unfortunately,
the producer wants. That's how they make money.
they want cheap.
Yeah, that's right. So, I guess to make it simpler for our listeners, is the difference between UHPC. If we were just looking at the ingredients, it would be like I guess what I'm getting at is you're being highly selective, top of the line, top quality material that you put in UHPC versus traditional concrete. We can roll with whatever. I mean, you can read articles all day long about what people throw in traditional concrete on purpose or not on purpose. I mean, in Japan, they throw their garbage in concrete. You can read about people throwing coffee in concrete. You're not
Yep.
doing that with what I'm getting at is you're not doing that kind of stuff with UHPC. So having this conversation with you as I'm thinking as we're talking, that is why we have problems with traditional concrete. Is the it's not necessarily how well, I guess it is how we're handling it. But what I'm saying is the ingredients that we use for traditional concrete is really the weakness of traditional concrete. Meaning,
Yes, sir.
the crappy cement that we're using, the crappy aggregates we're using, those are all things that make concrete not perform at its best. Versus UHPC, you're making sure that the material that you're using is high quality, so you don't have those issues. And you're also taking out the aggregate, which I think is could be I'm pretty sure it's a cause of some of the issues we're having today. Is we're using crappier aggregate than we used in the past, and that's just because we're running out of the good stuff. I think the performance of UHPC is it's
consistent.
Well, it's consistent, but I'm trying to think of the best way to say it is we're eliminating the problems of concrete, but you're adding the some things like in UHPC has, I don't think we mentioned, but it also has microfibers, right?
Yes,
in
sir.
it as well, which
It
traditional
does.
concrete, you're not putting any kind of reinforcement in it typically.
If you are a couple pounds a yard, this is hundreds of pounds a yard.
But I'm saying if you order UHPC, it's automatically in there. It's not an additive. Versus traditional concrete, we would say, hey, we want microfibers or macrofibers, which are usually a synthetic fiber. When you order UHPC, I know your product, but I assume all UHPC all have some kind of microfiber in it. Is that a quality of UHPC?
Almost. So there's a lot of cladding because they can reduce the thickness of a panel and the pull-out resistance of what attaches the panel to a building 40 stories up in New York or wherever it may be globally. They can reduce that. They have to put a fiber in. That porcelain plate thing, if you had fibers in there, it would bounce before it cracked easily. So all UHPC, for the most part, will have some type of fiber. For infrastructure and things with heavy loads, it will, as of today, the design guide that was released last October will specify high tensile steel fibers at a very high dose. So, but it's not like if you buy today, you got off the phone or you got off with me and you called up any of the competitors and you said, I want a cubic yard of your mix. It's not like it's going to show up with the fibers. The fibers would be separate on a pallet. You would mix the material and then add the fibers if needed. And you would add different amounts, Seth. Like if you're doing an overlay in the United States, at least, they want a 3% by volume, hundreds of pounds per cubic yard microfiber. If you're doing joint connections in the United States, generally it's volume dictated, although they're switching to spec driven, but it's a 2% by volume. It's like 265 pounds per cubic yard, almost 10% of the weight of the dry material. But then for cladding, they may use PVA fibers because it's a different different forces.
You're saying 200 pounds of microfibers?
265 pounds of microfiber, and it must be Buy America Act if it's federally or state funded. That's a big cost of UHPC that is quite often overlooked. I do want to make one correction briefly. You said all UHPC, everything is specific materials and such. We chose the path of just add water. So we're constantly getting the exact sand, the exact shape, size, lack of impurities, kiln, dried, take out to dinner once a week. Very expensive, over $100 a ton versus $15 out of a brick yard. There is a methodology that has been utilized, or there is a wave that we're choosing not to go in, which is some of the UHPC suppliers and even an organization in Florida, I forgot the acronym, they have open source recipes. And they basically say, hey, here's the price for my cubic yard of my material. You buy the sand, you can buy it from us, but you just need to buy the sand yourself. You need to buy the plasticizer yourself. And that makes me nervous. It doesn't make most of the country nervous, so I'm certainly biased. But technically, you're buying the unicorn dust, the unique binders that make it UHPC, the glue, and then the odds of you getting a consistent batch, and it shows that it doesn't happen as often as it happens. The water demand goes up and down. You get failed batches. Now, I'm not throwing out fear. I'm going off of hearsay. I don't have a document saying this, but it makes sense to me scientifically that if you're baking or making ribs and you constantly change one of the ingredients, you're going to get non-consistent results. So we've decided, I know Ductil's decided, I know Cientech, all of many individuals I respect in the industry, my competitors, to always use the same ingredient. So we always know, and you always know, what you're placing and what's going to happen to it in 1 day, 7 days, 28 days.
So you're saying you're saying your UHPC is like going to the grocery store and buying a cake mix in the box versus other, like what I prefer at home is from scratch.
Well, I made my cake. I invented my cake from scratch over 10 years.
Right. Yes. But it's the same. Yes. You get the same thing. Just like if you went to the grocery store, that cake mix boxes, there's hundreds of them on the shelf. They're all the same. So you just add, you're saying just add water to yours is essentially what you guys are doing. Yep. Okay.
Yes, sir.
All right. So we don't sound like too much of a Steelike commercial. Let's get off that topic a little bit.
Thank you.
So the cost and everything we talked about. So we've talked about this before on previous podcasts. You can go back and listen. I think we both agree in the short term, we're not going to see. I know you mentioned precast panels being UHPC and things like that, but we're not going to see total structures in UHPC. It's just too cost prohibitive. So, and you mentioned about repairs, and that's where UHPC is catching ground right now. I know you worked with RL McCoy on some bridge projects, right? Doing overlays and things like that. So that's where UHPC is used mostly is for repairs, and its unique ability to bind on existing structures, be it any material, right? It can grab onto any material. So that's why you're people that aren't familiar with UHPC or are familiar with UHPC is why you're not seeing it everywhere, specified everywhere. It's got specific uses because of it of the cost restraint.
It's too expensive. It's too expensive to build a bridge out of, but it's too expensive not to use it where it adds dramatic benefits and lasts 75, 100 plus years. So there's the balance, right? Too expensive to build a bridge out of, too expensive to not use it, meaning by not using it, now you're replacing things. Talk about carbon footprint when a bridge, is designed to last 50 years, and you factor in inflation and everything else. UHPC can be carbon negative after 50 years. So go ahead, sir.
So what did we do before UHPC? I guess what is it replacing? And I understand it works great for repairs and everything, but was it for instance a bridge? What were we doing before when we did repairs versus why we use UHPC?
Yes, sir. One of the number one failures across 60,000 plus bridges in the United States are the joint connections, where salts, chlorides have gotten in and have caused the degradation of the bars that were connecting the panels. The panels, in many cases, are still alive. So what we were doing was, number one, building the bridges with like 3-foot wide joint connections because we needed, based on the limited strength compared to UHPC, we needed a lot more material to glue those things together and to achieve the proper developmental length bonding of the rebar. So by cutting out that decay, you have a cavity, go to the dentist. The dentist isn't going to say, we're ripping out your tooth. They're going to get rid of the decay and fossilize it, encapsulate it, preserve it, repair it, harden it, so to speak, with a material that can handle the bite force. It can't be so brittle that it snaps like your tooth enamel. And we can make that joint 8 inches wide and 8 inches deep with dramatically less bar required. So right there, we've kind of shut off one of the major failures of bridges, which are not, many of them are the connection joints themselves. So what we were doing was using a lot more material. Again, carbon footprint. What we were doing was putting in a material unintentionally that had planned obsolescence that would then have to be replaced. And if we keep putting back the same material, the same problem's going to occur. Right. So we're going to replace that joint 3-4 times over the bridge cycle versus once with UHPC. That's what we were doing. If the bridge was degraded from chlorides and rutting and everything else by the ocean, there's a lot of salt, or freeze-thaw environments, snow, ice, chains in some parts of the world. Generally, you'd rip it out and put down another 6-8 inches of regular concrete that, guess what? Had chloride permeability sensitivities, had a lot of air entrained on purpose to hopefully give the water a place to expand, but it also allowed water to get in, freeze, thaw, spalling, cracking, popping. So we could do that whole thing again. Or we can, like the tooth, we can get rid of the decay and some of the bar if needed and replace it and put an overlay over it. We can put 1.5 inches, 2 inches over the entire frickin' bridge. And we've just encapsulated, depending on thickness, hardened, strengthened, but even without that, preserved, restored, and put down a material that can handle that abuse of real-world traffic or chains dragging on it, whatever it may be, that's not going to let water in. Ergo, it's not going to let chlorides in. So it's not going to freeze and thaw because there's nothing to freeze, right? That's what we were doing. And we were doing it with Portland cement. There was 100% Portland cement, and now we're asked to do it displacing 10 to 15% of that. If we have time, I'd like to quickly go there, but please check. I want to make sure I'm answering your questions.
Yeah, so before it sounded like for instance, a bridge repair, we were chipping out a large section and then pouring back traditional concrete, whatever they used on the bridge before. But
Yes,
what you're saying now is now with ultra high performance concrete, you have less chipping out, so less labor. You don't need as a big of a space to make the repair. So instead of a 3 foot wide, now maybe you can do it in what, a foot or
8
less?
inches.
8 inches. All right, so 8 inches, so less labor there.
Less bar. Much less
less
bar.
Yeah,
Yep.
less bar. Yeah. So yeah, so less material, less labor. So yeah, that makes sense for UHPC. Yeah, but we're getting near the end here. So what did you want to hit on before we left?
I just want to follow up on two people I respect, Dr. John Belkowitz and Dan McCoy. I've heard them speak. I've had the privilege of meeting Dan, spending some time with Dan. We tried to blow my stuff up with his gun safe and didn't have much luck, which is a yay. And all I want to say briefly is can't have two particles in the same space at the same time. There's a new policy to all cement manufacturers in the United States. It's not happening overseas. You have to displace 10 to 15% of your glue that you know what it is, and you've known what it is for 20 years with crushed lime. So we crush it. We make it smaller. We make it fine particles. Yay. The stuff is really inexpensive, but the price is going to go up. Number one. Number two, we're displacing some of that glue. So in closure, I just want to mimic what I believe, which is it's not a one-to-one replacement. We're all being sold on, it makes it react faster. If you read deeply, it can also hurt your long-term strength. So you get a little green strength at the expense of your long-term. That's frustrating. If you're taking out glue, you got to put glue back. If you do a one-to-one and you put the same amount of water in you've always put in, it's too wet, so you're lowering your strength. So there's the optics of how we're saving the planet by displacing some of this glue that, yes, absolutely burns a lot of carbon to make it cement. Let's put in crushed lime, which is really inexpensive, dirt cheap, pun intended. And now people are told it's one-to-one. They add the same amount of water. Well, if you're looking at 150 pounds per cubic yard of a powder that's not cement, things start to change a little bit. So I've spent 45 days testing and testing and testing so that in America, at least, where I'm forced to possibly make my material not as good, I figured out how to adjust it by replacing some of the glue with one of the other unicorn dust that I've been using. And I'm actually going to get a slightly better product. But my point is, build a bridge with PLC that has 15% less binder, being told publicly that it's a one-to-one displacement, the concrete quality goes down, the strength goes down. Now, instead of patching that bridge in 5 years, you might patch it in 3 years. Use UHPC. Talk to me in 75 to 100 years. So that's my whole true carbon footprint, optics versus science. Thank you, Dr. John and Dan McCoy, for helping me embrace the reality so I could make adjustments that are necessary.
Yeah, no, it's something we're all getting through. Yeah, I don't know what I've beat up Type 1L so many times on here, but it's got so many issues, and we just got to be. I'm starting to hear even from the architect and engineering community, they're starting to recognize that. And actually, someone reached out to me this week and had a submittal review where the engineer pointed out the possible finishing challenges you have with Type 1L cement mixes, and I was excited that we're starting to hear the design side of the community recognizing the challenges that we're having. So
yes,
that was refreshing. But All right, Bill. I think we covered it today. I'll put your contact information in the and when we release the podcast in the show notes, so people know how to reach out to you and learn more about UHPC. So thanks again for coming on the show. And folks, until next time, let's keep it concrete. And that concludes another episode of the Concrete Logic Podcast. I hope you got some value out of that episode and learned a thing or two. If you did, visit our website, concretelogicpodcast.com. Click on the show support tab and learn how you could be listed as a producer of an episode. Again, that's concretelogicpodcast.com. Click on show support tab to learn how you can support the show. And as always, Mike Dunton will take us out.
Couple hours before the sun comes up. Open up the side, put some diesel in the lights, and wait till the trucks roll up. Yeah, this ain't how most folks live their lives, dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and mud. We work hard for a dollar, give thanks to the Lord above. Never make a man do something you can't prove. Hard work calls for a drink or two. Expect more, it's written in our blood. With wood, iron, and mud. From the swamps to the city, from the Lone Star heat to the woods of the Georgia pine. Good old boys and girls who ain't afraid of getting dirty for a clean time. And if you want to see the fire in a grown man's eyes beneath the hot summer sun, find the wild-eyed boys clocking days and nights, working hard to get that job done with wood, iron, and mud. We work hard for a dollar, give thanks to the Lord above. The color of our collars ain't white or blue, we're all gray collar through and through. Expect more, it's written